It's a pleasure to be here tonight and to see so many people interested in learning about deep learning. Um, this is a fundamentals talk, so we are covering things from the ground up. You can find the slides for tonight at the link that's on the screen here, my website /talks. And that has all of the embedded links that I'll be talking about today, including half a dozen Jupyter notebooks that won't get nearly as much time as they deserve during this hour. So we are going to talk about the historical antecedents that led us to today, looking at biological and machine vision as a case study, and then quickly going over the building blocks that you need to be applying deep learning today. We are going to talk at a high level about the theory of artificial neural networks, including deep ones, just enough to make the concepts make sense. And then we'll talk about contemporary applications of deep learning, convolutional neural networks, LSTMs, what we do at Untapped with these methods, and deep reinforcement learning. So let's start with the case study. This is a trilobite. Trilobites developed the ability to see with a very rudimentary light sensor 543 million years ago. That ability to detect things moving in the distance has myriad biological benefits. So you can identify sexual partners, you can avoid predators, you can identify prey. So all of these things all of a sudden made life on Earth capable of a much richer variety of behaviors, which led to something called the Cambrian explosion. So this is showing 543 million years ago, before the trilobite could see, there were a negligible number of genera of species on the planet, genre or groups of species. And then you can see there was this explosion leading us to today where we have many, many thousands of genera of species on the planet. Fast forwarding ahead quite a bit in the interest of time to 1959, we have some famous studies by Hubel and Wiesel, who at the time were postdocs at Harvard and were later awarded the Nobel Prize in Medicine for their work recording from the single cells of cat neurons. So your visual system works by signals going from your eye directly to the back of your head. And the simplest processing happens right at the back there. It's called V1. So Hubel and Wiesel were like, oh, well, the eyes connect. They knew neuroanatomically the eyes connect to that part of the brain. So they put electrode recorders into those neurons, and they showed the cat stimuli of other cats, of fish, and they were incredibly disappointed that they had no activation in these neurons whatsoever. By chance, they noticed that moving one of these slides off after an experiment, they left the recording device on, and they caught the cat looking at the edge of a slide as it moved out of its field of vision. And that's how they discovered that that part of the brain was not processing these complex images, but processing edges. So this is an example of an edge stimulus. You can see here, they were then able to discover that very specific neurons, can you see my mouse cursor on the screen? Okay, so you can see here that this, at a 45 degree angle, this edge stimulates the neuron quite a lot. And then at orientations, even just slightly away from 45 degrees, it fires quite a bit less. And then at 0 or 90 degrees, this neuron does not fire at all. And that behavior follows a normal distribution. So those are the initial, so the very simplest, the first neurons are processing just edges. And then they feed up into more complex cells that are detecting corners. And then those mid-level cells report into higher level cells that eventually are able to recognize things like fish and other cats. For example, in the human brain, we have parts of the visual cortex that are designed specifically for processing other humans' faces. That area is called the fusiform face area. And there's areas for color and form, for motion, and all of those relay from the very simple structure, the V1, which is just detecting edges, just like in the cat, into corners, into these more complex shapes. So, we'll get back to that story in a second. So that's how we see biologically. The first attempt to use a machine to capture the physical world was Leonardo da Vinci with his camera Obscura, or at least it's one of the earliest surviving cases. So in the 15th century, he built this device it's something like a rudimentary camera. In the computational world, Larry Roberts was the first person to try to use computers to make sense of captured visual images and try to identify them with his effort called Block World. And then, primarily, through the 20th century, the predominant methods for machine vision involved explicit coding of features in the image. So if you wanted to identify a face in an image, then you would have to come up with clever ways of identifying what kinds of characteristics does a face tend to have in an image, or what kind of characteristics does a house tend to have in an image, or a cat or a boat or whatever. Viola and Jones had this very simple algorithm, these dark and white boxes, these two varieties of them, that ended up being incredibly accurate identifiers of human faces in photos. And this algorithm was the first machine vision algorithm, a face recognition algorithm, to go into production. It went into Canon cameras around 2006, and that was the beginning of us seeing it now. Your iPhone or Android phone does it. Everyone's camera does it. Identifies the face and focuses on that. But at the time, it was a completely novel invention. An alternative approach to explicitly coding all of the features in an image for machine vision is to take the method that the biologically inspired method. So this neurocognition developed by Fukushima in 1980 is inspired directly by the Hubel Wiesel cat recordings that I showed earlier. So he surmised that you could build a computational system that builds up edges into corners into more complex images, like faces and houses and what have you. Now, there were a few things that he was missing. Computational power, data, a sufficient amount of data, and also some other things like the backpropagation algorithm that we'll get to later on. And by later on, I mean in this slide. Forgot that slide was right there. So Jon Krohn, who's based here at NYU and runs the Facebook AI Research Lab, which is alongside Google, probably the most prestigious place you could be doing AI research. In the 90s, he was at AT&T Bell Labs, and he developed a very similar kind of network to what Fukushima was proposing. And what he was doing was he was identifying digits, so these are the MNIST digits from 0 to 9, for the US Postal Service. So up until the 90s, every zip code on every piece of mail had to be read by a human. And this process automated it. And this is, I'm going to dive right into this right here to kind of show you how deep learning works. So you input at one end of the network the raw images, so the digits 0 through 9. For some reason in their paper, this is directly from their paper, they used the letter A, which was never one of their input digits. And then those feed into low-level feature maps that are detecting edges, and that feed into more complex shapes until an output layer identifies whether this is in fact the digit that the network is guessing, and then provides feedback that allows the network to learn. We'll talk about that a bit more as we go on. It's just a taste of what's to come. So you can see here what these images are showing is if the letter 3 is input into this network, what the neurons in each layer of the network are seeing. So you can see that the very simplest, the very earliest layers are detecting edges around the corners of the 3, and then as you move up further into the network, the representations become more complex until the very end the network guesses, yes, this is a 3. After that US Postal Service case, there was an AI winter. So researchers in the neural network space were unable to identify any other commercially meaningful applications and no real interesting research. So funding dried up. There were only a handful of labs that continued to do this research. NYU was one of them, University of Montreal, and the University of Toronto. The Canadian government, where I happen to be from, not from the Canadian government, the Canadian government continued to fund this research, but the academics who were working on it had to publish under kind of secretive terms. They couldn't use words like neural networks because that would doom them. And that was kind of the state of play from the late 90s through to 2012. To describe what happened in 2012, I need to tell you about the ImageNet competition. So the ImageNet competition is the standard way today of assessing the performance of machine vision algorithms. So it has 14 million images across 22,000 labeled categories. So here are some examples of the images. So this is a picture of a mite, and some algorithm has guessed that this is most likely a mite. But it's not super sure. It also thinks that there's a reasonable chance this is a black widow or a cockroach. In this image, there is a picture of a container ship, and the algorithm is very, very sure that this is a container ship. So it's assigning a very high probability to that category. And then there's some chance it's a lifeboat and basically nothing else. You can also see that sometimes it misclassifies. So here it has identified a convertible, which seems actually like a pretty good job, but the human who labeled this particular image labeled it as a grill, so this is considered wrong. Similarly, this Dalmatian image is wrong because the human labeled it as a cherry. So you kind of get a sense there of how this works, right? So in 2012, this competition was blown out of the water by a deep learning algorithm created by Jeff Hinton and his team at the University of Toronto, and now Google. So you can see here the error rate on this ImageNet competition. It was 28% in 2010, 25% in 2011, and then in 2012, when Jeff Hinton introduced his algorithm, he cut the error rate enormously. And what this is showing is that the winning algorithm is in purple here, is a deep learning algorithm. And every year subsequently, a deep learning algorithm has also been the winner. So it completely transformed the machine learning, the machine vision space. Prior to 2012, everybody was explicitly coding features in the kind of Viola and Jones, black and white boxes type of way. So this is just another way of showing the same kind of information where you can see the entries with the traditional explicitly coded features are shown in blue, and Jeff Hinton's team introduced their algorithm here, which blew all of the other algorithms out of the water, and subsequently pretty much all of the submissions to the competition have been deep learning algorithms. you can also see here that in 2015, the machines eclipsed human performance on the task. So here's a look at that network that Jeff Hinton and his team submitted in 2012. It's named AlexNet after the first author, Alex Krizhevsky. And you'll notice that this structure is very similar to Jan LeCun's from the 1990s. And then you can see kind of examples of at each level how images look. So you can see the edges, just like in a cat brain or human brain at the lowest level. Then some textures in the third tier. In the fifth tier, it's starting to identify objects. And at the very top, it's identifying whole object classes. So if this structure was so similar in 2012 relative to what they were doing in 1998, the network structure, what kinds of things changed in that time that enabled deep learning to be so much more powerful? Processing power, that's right. So CPUs became a lot faster, and then they also pioneered, with this paper, the use of GPUs, which can do matrix multiplies much, much faster than CPUs. And so they split all the data into two channels and then had two GPUs do this processing. What else? Data, yeah, that's another big one. So yeah, they had much, much, much more data. The MNIST digits, there's 70,000 training cases, and for ImageNet data, there's 22 million. So many orders of magnitude more data available. And then on top of that, there are some smaller technical advances that we'll talk about in a bit, but primarily they're using the same approach. So since 2012, all the major software companies have started using deep learning for many of their applications. Facebook uses it to recognize your face in photos in Facebook. Tesla uses it for their self-driving cars. Google uses it for their inbox auto replies. They use it for their searches. They use it in hundreds of different ways. And Siri's voice recognition went from 95% accuracy to 99% accuracy in the last couple of years by switching from traditional explicitly coding approaches to using deep learning. A really fun example of deep learning is this LSTM that wrote a film, Sunspring, last year. So they fed into this network hundreds of blockbuster film scripts and then had the network write a film. And we're going to watch it, like a minute of it, if I can figure out how to do that. So this must have been enormously fun to... Wow, ads. Here we go.
Principle is completely constructed at the same time.
It's all about you to be true.
You didn't even show me with the rest of the base.
I don't know.
I don't care.
I know. It's a consequence. Whatever you need to know about the presence of the story. I'm a little bit of a boil.
I don't know. I need you to explain to me what you say.
What do you mean?
Because I don't know what you're talking about.
That?
So you can see that the words kind of make sense next to each other, but the dialogue as a whole doesn't really make sense. And then there's just one more kind of part that I think is really funny.
I was a stranger and promised to be so happy. I was a beautiful day. I was tall and talking.
I just wanted to tell you that I was much better than he did. I had this father. I couldn't even tell.
Truth was so long ago. I was so happy and blue. I was thinking of you. I was a long, long time. I was so close to you.
So essentially, it's taking all kinds of archetypes and common language from many blockbuster films and blending it into its own kind of creation. So to build your own movie script with an algorithm, what would you need? You can build it. You can build a deep learning network on your local machine if you have a small amount of data. You could build your own server with some GPUs from a few $100s using some older GPUs to a few $1,000s using state-of-the-art ones. I think the easiest thing to do is to spin up instances on AWS or Google Cloud Platform. Google Cloud Platform just last week released GPU instances, so those are in beta. Prior to this talk, I always had to say, if you want to do work with GPUs, you have to do it on Amazon. But that's no longer true today.
I think there's a Kaggle competition that if you sign up for, you can get some free time.
Oh, really? Apparently there's is it the medical imaging one?
This one is a YouTube tag.
A YouTube tag?
Yeah, it may not apply to the GPU instances, but maybe.
That's a great tip. There's a Kaggle competition that involves tagging video YouTube clips, and if you sign up for that, you get free credits on Google Cloud Platform. Thank you. So the 4 most popular libraries for doing deep learning work are Caffe, Torch, Theano, and TensorFlow. They 3 of the 4 of them are coded up in Python. Torch uses Lua, which I've never used. I've never used Torch, and I don't talk about Torch in this talk. All of them work on pre-trained models, but Caffe and Torch are best for that kind of work. So if you want to be using some big, bulky model that's already been trained to do lots of generic machine vision, and then you want to train it to identify something specific, like you work at a retailer and you want to be able to automatically recognize brands of shoes or celebrities or something, you can use the bottom of all of the pre-trained network, and then in Caffe in particular, you can very easily train just a top layer to take advantage of all of the existing infrastructure. All of these work in parallel on GPUs for data. TensorFlow is far and away the best. If you want to have your model work across many GPUs, TensorFlow is far and away the best. Pardon me? Your vote is for PyTorch? The guy converted to PyTorch? Oh, you're saying there's a Python package for calling Torch? Okay, I didn't know that. That's cool. So there is, it's tougher to get into the source code for Theano or TensorFlow than for the other languages. If you're going to be training recurrent neural networks, which are primarily used for language stuff, we'll get to that at the end of the talk, you'll want to be using Theano or TensorFlow. And for getting started, higher level APIs are available for Theano or TensorFlow. So we'll talk about both Keras and TF-Learn in this talk. I also maintain a webpage on my site, so myname.com/resources. I have categorized groups for getting started in deep learning or keeping up with cutting edge papers. It's a reasonably comprehensive resource for getting going in deep learning. So let's do just a touch of theory so that we can make sense of the applications. Artificial neural networks are inspired by biological neurons. So this is what neurons look like in animals, including in you. You have billions? Yeah, I think it's safe to say billions of these, with trillions of connections. So the way that it works is the dendrites take input from thousands of other neurons in the brain or in the body. And if those inputs cause the electrical charge on the cell body to go below a certain level, it causes a signal to be sent down the axon to the end of the neuron, and that then stimulates thousands of other neurons here, creating this network. So that's the inspiration behind artificial neural networks, which work in fundamentally the same way. So the perceptron introduced by Rosenblatt similarly takes in multiple inputs. Here is just 3 as an example, but it could be thousands of inputs into a cell body that does some kind of computation. And if the results of that computation are above or below a certain threshold, then you'll have a binary output of 0 or 1 respectively. So, you're essentially taking input from many, many neurons, and for example, a very simple example would be to sum all of those results together with some learned weight, and then if the sum of all those inputs is less than a threshold, say the number 5, then the output from this neuron will be 0. If the sum of the inputs is above 5, then the output is a 1. Does that make sense? So this is an action potential, which is the way that a signal is transmitted in a biological cell. So it is binary. It always has the same amplitude. It's either on or off. It doesn't vary. And the perceptron has the same effect. So up to the certain threshold, which in this case is 0, the output is 0, 0, 0, 0. And then as soon as the sum of the thresholds, or the sum of the inputs goes above 0, the output from the neuron is 1. So it's this binary output again. The problem with this kind of approach is that once you start layering the perceptrons together into a multi-layer perceptron, like a deep learning network, then small changes in inputs can have a dramatic effect on the output of that neuron. So, you're approaching the threshold, nothing happens, then you hit the threshold, and bang, the output switches. So that's a very coarse, it's a very coarse way of thinking about learning. And it makes it difficult to then learn at the output layer. So the modern way of having these functions work is to use a gradual gradation. So as your inputs vary, so too do your outputs vary gradually. And so the sigmoid neuron was a very common way sigmoid function was a very common function inside the body of artificial neurons for a long time. It ranges, just like the binary output, it ranges from 0 to 1. Tangent neurons are the similar kind of concept and a similar kind of shape, but they actually vary from -1 to 1, so you get slightly different effects. However, since 2010, the norm has become to use rectified linear units, which are relatively simple. They clip output at some level, at some bottom threshold, except for leaky ones, which kind of clip it on the right. And then otherwise, they're simply linearly. So they capture a lot less information than the sigmoid or the tangent neuron did. But they have a couple of advantages. So one advantage is that when you get stuck up at the top or the bottom of a tangent or sigmoid neuron, it's very hard to learn here because large changes in your inputs have very small effects on your output. The other advantage is that the partial derivatives that you need to do this learning, or that are predominantly used to do this learning and are largely beyond the scope of this lecture, are much, much easier to calculate on a straight line than on a slope. So even though there's less information captured in each individual neuron, you can have many more of them processing a lot more quickly, and therefore ReLU units are much more efficient. So We know what artificial neurons are. Now let's network them together. So returning to the MNIST digits, let's, I don't know why that slide was there. I must have had a good reason. Oh, right, I know why. Okay, so let's imagine these MNIST digits again. So the MNIST digits, every single one of the stimuli is a 28 by 28 pixel image. So it has 28 squared, I think, is 784. So there are 784 pixels that are forming input data in each of the cases. So the way that you structure your network is you have 784 input neurons. Each one, this is a very, very simple way of solving this problem, but you can have just each pixel in the image linear. You can take that two-dimensional array and just flatten it into a linear one-dimensional array and use that as the inputs, and the relative darkness of each pixel is the input in each of these 784 neurons. A fully connected or dense layer is a very common and relatively simple kind of structure to explain in neural networks. All it means is that every single neuron in the preceding layer feeds into every single neuron in the next layer. So in this example, this neuron here, which is one of 784 inputs, obviously abridged for the purpose of illustration, feeds into all 15 neurons in this hidden layer. Any layers that are not the input layer or the output layer are called hidden layers. So here we have 15 neurons in the hidden layer. So there's 784 times 15 connections between these two layers. And then the single hidden layer here is connected to 10 outputs, also fully connected. So you have 15 times 10, 150 connections between these two layers, and they're actually all shown here in the diagram. And each of the outputs represents one of the possible digits. So you have digits 0 through 9, you have outputs 0 through 9. So those are the classes that the network is trying to predict. This is a very simple model, and I hope that that explanation made sense. And even this very simple model would be able to learn reasonably well. So basically, it starts with random weights at each of the connections between the neurons, and then as you show it more stimuli, it learns how to adjust those weights so that, for example, if the digit 7 always had a dark pixel on one of the images, this is an oversimplified example, but then it would learn to strengthen that weight between the input of that pixel through to the output of 7, and that's how the network learns. I'm going to illustrate it with a fun demo. So this is TensorFlow Playground. It's so much fun. Let's switch to ReLU neurons. This allows you, I highly recommend this as a kind of a first step for learning how to play around with networks. So here we have a super simple network. All it's taking in as inputs are the position along the x and y axes, and we have a classification problem that we're trying to solve here. We're trying to distinguish the blue dots, which are coded as 1, and the orange dots, which are coded as -1. We're trying to distinguish those two groups from each other. So, and we're doing that with just a single neuron in a single hidden layer. So this is a fully connected network. We have both inputs, so the x-axis and the y-axis, feeding into this single neuron, and then it inputs, outputs some value. So that ends up working exactly like a linear regression model, where all you can do is fit a straight line. If you make this more complex and add a second neuron, you're capable of this slightly more complex shape. If we add in a third neuron, all of a sudden you can make this polygon. And so this ends up actually classifying pretty correctly. It does a really good job of this classification task, although it's a very simple classification. So what happens if we throw a much more complicated problem at it? Well, I've played around enough with this to know that this network will solve it pretty well. So we're adding in layers into the network. Now we have 4. If we keep it this simple, it will have a very difficult time coming up with some kind of weightings between the neurons to solve this algorithm, or to solve this classification task. And interestingly, so you can see in each of the layers what the kind of pattern that the neuron is looking for. So you can see once again that the lowest layer is looking for edges. Let's make this more complex. So we're adding 8 neurons into each of the first 2 hidden layers, and then 4 neurons into the 3rd and 4th hidden layer. And now all of a sudden, we're able to learn pretty well. So, and you can see very simple edges in the first layer, corners in the second layer, and then more complex representations in the 3rd and finally 4th level. It'll get going even better. So here it keeps learning. There it goes. It just figured out. It just recalibrated enough. So does that make sense? So that gives you a sense of how these things work. Yes, sir. Right, so you have a random initialization of the weights, and there's, I'm not going to go into this in detail in the lecture, but the most naive way is to just assign random numbers, or random numbers on a normal distribution. But then there are more clever ways of going about it depending on the problem you're looking to solve. And then as the network learns, it starts to, so you can see here. So I'll start, when you refresh the network, all of these weights are relatively small numbers between the neurons. And then as it learns, it strengthens some of the connections and doesn't strengthen the others. So you can see here, this dark orange line, that's a very strong negative weight. These dark blue lines, that's a very strong positive weight. So does that make sense? Exactly. So based on, so it's being fed stimuli, it's being fed some subset of these outputs at each iteration. So now it's done about 800 iterations. And at each iteration, it's fed a different subset of these stimuli. And it's given feedback as to whether it classified them correctly or incorrectly. And based on that, it sends a signal back to update the weights to better represent correct classifications. Yes? Is there a good rule of thumb for changing learning rate or initial learning rate? I'll get into that in a second.
Another question.
Yes?
So more outputs gives you better, more complex recognitions, but how do you decide how many layers to have?
Playing around. To some extent, you can, so the outputs are a function of how many classes you're trying to predict. You don't have any wiggle room there, really. So if there are 10 digits on our hands, and therefore in the zip codes, then you have 10 classes that you're trying to predict as an output. In this case, it was a binary output. For the ImageNet recognition, they typically do that with 1,000 classes, so then you have 1,000 outputs. For picking the number of hidden layers, it's a function of how much processing power you have, and the same thing with how many neurons in the layer. It's you kind of fiddle around, and you can peruse the existing literature for similar types of problems to try to identify what might work, and then playing around. There's similar to the learning rate question that you asked. And the number of layers or the number of cells in a layer, there are many hyperparameters in these neural networks, and you kind of just follow the best practices that other people have set out before you until you've developed enough of an intuitive sense of yourself to make your own changes. Okay. Right. So a deep network is very simply a neural network with 3 or more hidden layers. We are going to go through an example quickly of a network built in TF-Learn, which is a higher level API on top of TensorFlow. And it's kind of the simplest way to learn about building neural networks. So all of these are linked to from my slides. And can you guys still see that everywhere, kind of? So you input the dependencies, the TF-Learn library. For famous data sets like the MNIST digits, there are simple functions for importing the data. If you were importing your own data, this would obviously be more complicated. And then, as with any machine learning problem, well, any labeled data machine learning problem, you are going to split your data into a test and training split, and separate your labeled outcomes y from your input features x. So the outputs y are digits 0 through 9, and the inputs are the pixels in the images. So as we said earlier, there are 784 pixels in an image, so you can just feed those in as a linear array in your input layer. Then that input layer feeds into a fully connected layer that we call dense 1. So dense and fully connected are synonyms. And we have somewhat arbitrarily, though often it is squares of 2 that are used here. So 64, we're using tanh neurons. We could be using ReLU. We're regularizing with L2, which is something I'm not really going to talk about in detail now, but anyone who's doing machine learning will be familiar with L2 regularization. And then the weight decay is a parameter on the regularization, which we're also not really going to talk about today, but it enables you to avoid overfitting appropriately. So we have that that first hidden layer. It feeds into a dropout layer, which is another way of regularizing and avoiding overfitting. Essentially what it means is that on each iteration of learning, you remove at random some set of the neurons. In this case, we are retaining 80% and removing 20%, although a more common convention is 50%. And the reason why we do that is that it prevents overfitting by having too much dependency on any single neuron in the network. So these are actually still one layer, okay? And the dropout is just a regularization of the first dense layer. And then that feeds into the dense 2 layer, which again has the same parameters as the first layer, 64 neurons, they're all tanh, L2 regularization. And then again, we're using dropout to regularize. And finally, you output in what's called a softmax layer, which is a very common way of identifying the probability that one of the digits is higher than the other 9. And so here we have, so there's an input layer with 784 neurons. There's 2 dense layers, each with 64 neurons, and then an output layer with 10 neurons doing classification. So this is a very, very simple network. I hope that all makes sense. And so that's specifying all the parameters. And yeah, then you actually do the training. So we're specifying that we're going to use stochastic gradient descent. and that instead of, all this is doing is saying, instead of, what we're considering the answer to be correct if the correct answer is in the top 3 guesses of the network. And then finally here in this in this line of code, you're actually specifying the network. So you're tying all of the above information together, and yeah, training it down here with this model fit. So you can see it attains this very simple network has 99% accuracy. 99.0% accuracy. But that's on the top 3. It's the top 3, right? Yeah. So that's cheating. All right, so synaptic. So I'm just going to go over a few key concepts quickly. So synaptic pruning is that thing we actually talked about with the weights already. So in a human brain, when you're born, you have way more connections between your neurons than you do now. So it's kind of like a random initialization. You just have all these connections, and you're unable to see. You don't know the sound of your mom's voice or the look of your dad's face. But as you get repeated stimuli and you learn, oh, food is like, you get positive feedback from food or cuddling, whatever, that enables synaptic pruning, where many of the connections are regarded superfluous. Many of these random initializations are just thrown away, and some subset of those are retained and have these strengthening weights that allow you to recognize faces and voices and learn language and everything in your life. Stochastic gradient descent is used typically to learn these networks. Backpropagation is such an important thing here. It's fundamental. It's what made Jan Kuhn's networks in the 80s and 90s start to work, and it's what distinguishes those networks from the neurocognition of the 1960s. Backpropagation is how neural networks learn today, always. And we don't really have time to go into the detail, but it uses a set of equations and partial derivatives over those 4 equations to learn how to adjust the weights in the network based on the output. So you have forward passes that convey the stimuli, say the pixels in the MNIST digits. The forward pass passes through the network, through all the layers, to the end where it either correctly classifies the digit or it does not. If it does not correctly classify the digit, then you backpropagate through the network. Actually, if you're correct or incorrect, you backpropagate through the network to slightly adjust the weights to say, okay, well, we were correct, and we can do these little weights better, for next time. We were incorrect, and maybe this change here will alleviate some of that incorrectness. So that's essentially how it works. And that little demon there is supposed to symbolize how that works. It's from Michael Nielsen's textbook, Artificial Network. I can't remember what the textbook's called. It's by Michael Nielsen. It's online. It's wonderful. It's a great introductory text to deep learning. We talked about regularization and overfitting briefly. So if you only have, so this is a very simple illustration of overfitting. If you only have 1 parameter in your model, it doesn't fit this parabolic data very well. If you allow for, if you have 2 parameters in your model, you can fit it very well and it generalizes well. If you have, a dozen parameters in your model, you can fit the data perfectly, but it doesn't apply very well to new cases. So with neural networks, where we have thousands or millions or billions of parameters being learned, it makes it very, very easy to overfit if you're not careful. So classic L1 and L2 regularization, dropout, or artificially expanding your data set. So for example, if you have the MNIST digits, there's only 70,000 stimuli, you can rotate the digits slightly, and they're still 7s or 8s or 9s, but they're new stimuli for you to train the model with. don't really have time to go into this at all. It ties into the learning rate thing that you were talking about, or the number of, there's so many hyperparameters that you can tune in a network. And I have a summary blog post on how to go through this step by step to optimize your network that you can link to from these slides. One of the wonderful properties about neural networks is that they are proven to solve any continuous function. And the unstable gradient is an important property of neural networks. It's actually it's a bugbear. It's a problem. So the more layers that you add into your network, the more difficult it becomes to backpropagate error into the early layers of the network. So if you have a 4-layer network, the 4th layer is right next to the stimulus classification of correct or wrong. So it is fairly easy at that top layer to learn, well, we need to make this adjustment to be better. But then once you get down to the 3rd, or the 2nd, or the 1st layer, the information is diluted. And so that's typically what happens. So it's called a vanishing gradient. So it becomes harder and harder to learn at the early layers, the deeper your network becomes. Alternatively, if you parameterize it differently, you can end up with an exploding gradient where it's learning way too much at the bottom. But I actually don't know how to configure it to do that. And all this is showing here is that in hidden layer 4, learning is 2 orders of magnitude faster than in hidden layer 1 in this random network. I can't remember where I got this from. That said, the leading edge of neural networks, of deep nets, is getting deeper and deeper. So 2012, we talked about the AlexNet coming out. That had 8 layers. The winning network in 2013 and ImageNet also had 8 layers. But then 2014, 19, 22, and in 2015, 152 layers. So an order of magnitude change. These guys, they're at Microsoft Research Asia, Haiming Le, and he left and is now at Facebook in New York, I think. And his ResNet was, it was not as dramatic as AlexNet coming out in 2012 with deep learning at all, but you can see here there's this huge difference. And so they have a number of tricks for avoiding the vanishing gradient problem, and they are also just throwing a lot of compute power at this. There are a couple of classic deep architectures. So we're going to talk about AlexNet and VGG quickly, and I'm going to show you some sample code. So essentially, all of these networks have what are called convolutional layers. AlexNet and VGGNet are very similar. So you can see the 8-layer network is here, AlexNet, and the VGG network is 19 layers. But they're very similar. So they have convolutional nets alternating with pooling layers. All that pooling layers do is they make things simpler. So they might take 4 adjacent neurons that are making a little square like this. And then it takes the maximum value of those 4 neurons and brings it just as one value into the layer. So it reduces the complexity, or it reduces the amount of data. It divides it in 4. So you're essentially the same kind of, so these have the same kind of structure, convolutional layers alternating with pooling layers, and then at the end, fully connected layers, just like we've been looking at throughout this lecture, where every single neuron connects to every single neuron on the next layer. And we've also talked about softmax briefly. The only kind of layer here now that we haven't covered is the convolutional layer, which we'll get to now. So returning back to that, the cat recording idea, cat cell recording idea, and hierarchical neurons with low-level features turning into corners and more complex shapes, including in the human brain. As we discussed, AlexNet works in that same kind of way. And when you're seeing any of these neuron images that I've been showing you through this lecture in the vision recognition networks, all of them have been convolutional layers. And the convolution is just a kind of operation. It's just a mathematical operation. And essentially what it allows you to do is for an image, say an image of a kitten here, a kitten's head, that image has, in addition to pixels in height and width, it also has 3 color layers, red, green, and blue, right? So your convolutional layer has this structure of, it matches the height and the width and of the image plus the 3 color layers as depth. And then it simply has this patch, this filter that scans across the image, and it means that the convolutional layer is invariant to the position of the object in the image. So you might have a filter that becomes very, very good at recognizing cat ears or cat eyes, I guess eyes in general. And it doesn't matter where that eye or ear is in the image because this patch scans over the image. I hope that kind of makes sense in a hand-wavy way. To help make that concrete, there's this great, well, I'm going to mute it, this great video of how the convolutional layers work. So in convolutional layer 1, you have, so here we're trying to identify different classes of images. These are ImageNet images. It's a lot of the images are dog breeds because I guess there's a lot of those on the internet. So here this is an image of a Yorkshire Terrier, and the network is guessing with 89% probability that this is a Yorkshire Terrier. And the ones that the incorrect guesses are other kinds of terriers, so that's pretty good. And you can see in this so this is showing across the top the layers of the network. So convolutional layer, pooling layer, convolutional layer, pooling layer, convolutional, 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 pool, and then 3 fully connected layers, and then a softmax layer assigning a probability. And you can see that in convolutional layer 1, the neurons are detecting the edges primarily in the image. And then as you move, so here you can see it's detecting Jason Usinski is the speaker here, and it's detecting the edges of his face. And he shows that directly here by passing this image over. So you have neurons that are specifically detecting edges, right? And here's an illustration of what each one's kind of optimized for identifying. Once you move deeper into the network, like convolutional layer 4, you can see that there are neurons. First of all, there are many, many more neurons in this layer. And these neurons are specialized to, for example, recognize his face or recognize the wrinkles in his shirt. There are other ones for recognizing text. So you get the idea, right? In the same way that biology is hierarchically building up, so too are the machine vision algorithms, and they do that on their own. There's nothing telling them to create that kind of structure. That kind of structure is inherently there to be recognized, and the machine vision algorithm, just like the biological one, teases that out. I'm running out of time, but just want to show you guys that there. So I put together or collated all network examples of how you can build that AlexNet that we've talked about a number of times in this lecture. So there's the code here for building that. It's exactly like we were showing in those images. Convolutional layers followed by max pooling layers, a bunch of convolutional layers, then some fully connected layers at the end, right? And this is a different data set. I didn't train it very long. Should have trained it for longer. Only at 37% accuracy, but it would have gotten better. And then similarly, The same kind of network for VGG. So theirs is identical, except it's deeper. So you have more convolutional and max pooling layers alternating, again followed by fully connected networks at the end, fully connected layers. And this one you'd have to train even longer, but the results would be better than with AlexNet. So you can try those out. You can clone that code from my Git repository and try that on your own with TF-Learn. If you want to do it with TensorFlow, you get a lot more granularity in the kind of parameters that you can specify in the model. But I'm just going to show you that it basically becomes quite a bit more work. You need to specify a lot more in the model. So it's not as straightforward as TF-Learn, where you can just say layer, 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 how many neurons you want in each layer. You're all of a sudden having to specify many more parameters about each layer. So it ends up being more code, but you can be more specific. So this ends up having 99.0%, 99.1% accuracy on the MNIST digits. So that's pretty cool. And another great thing about TensorFlow is you have this tensor board for assessing how the accuracy in your network improves over time. It's kind of plug and play. You can also be doing it in Theano instead of in TensorFlow, and I don't know. And then so I have a notebook for you to explore that as well, and you can see, oh, actually this notebook is really long. So this notebook, it gives you a sense of, so you have to define the layers here at the top, and then you make a very, very simple shallow architecture at first with just a single hidden layer. And basically what I do is over the course of this notebook, I go from training this very simple network that has pretty good accuracy, 97.8% accuracy on the MNIST digits, and then over the course of this whole notebook, I make the networks more and more complex. I play around with various parameters that represent modern best practices, and in the end, go from 97%-ish accuracy to 99.6% accuracy on the MNIST digits. So you can look into that in detail at home. And then finally, I highly recommend, because we do this actually at my company, is using Keras as a higher level API to call on TensorFlow or Theano. And it's just a simple one-line parameter in a config file to change which one you're calling on. And Keras ends up being a really nice middle ground between the simplicity of TF-Learn and the complexity of the models that you can build in TensorFlow or Theano. So finally, I have a Keras notebook that shows you how to build the same kind of convolutional nets that we've been talking about for the last 10 or 15 minutes in Keras. So this kind of work, these kinds of convolutional nets are being used to identify tumors with great accuracy. Jeff Hinton has said that we should stop training radiologists today because it takes more than 5 years to train a radiologist, and within 5 years their job won't exist. Here's a great notebook for doing that. There's a Kaggle competition that I linked to here, a different one. The Data Science Bowl this year, which is kind of their premier Kaggle competition. It's for identifying nodules in lung tissue. And then finally, I'm just quickly going to say you can use Caffe to do transfer learning. So they have this model zoo of all of these existing pre-trained networks. So depending on what kind of classification you'd like to do, you can use that existing network that's already been trained over many weeks on enormous computers, and then you can just retrain the top layer to do whatever kind of classification you're looking to do for your specific task. This TensorFlow for Poets code is a really quick tutorial that shows you how to do that kind of transfer learning. Of course, the same kind of thing that works for images also works for videos. So you can, in real time, make predictions of what a video is seeing. That's similar to the kind of YouTube competition that you're talking about, labeling images. So we don't have time to talk about this in detail, but LSTMs, long short-term networks, are kind of recurrent neural network that work for processing natural language, and those are the kinds of deep learning networks that were used to create the script for Sunspring that we watched in the beginning. And just like the machine vision applications went through winters and ran out of funding, the recurrent neural networks in this parallel sphere, speech recognition, underwent the same kind of winters and disillusion, and then subsequent redemption, where now, for any kinds of translations, for example, the neural network outperforms the traditional methods and is approaching human capability. We don't really have time to talk about this in detail. Vector space embeddings are really incredible, but again, don't really have time to talk about that. They understand language. So, for example, my company, we recognize job applications, and we try to identify the best role for you to apply to. And we learn the hiring managers. So, we have clients like big banks, JP Morgan, UBS, Credit Suisse. They make hundreds of decisions on applications that come to them, and our algorithms learn the preferences of what they're looking for in those resumes. These kinds of vector space embeddings allow us to do this with much less effort. So prior to this, we might have had to explicitly code that we wanted verbs like oversaw, directed, supervised, coordinated to be considered to be similar kinds of words showing managerial prowess in the resumes. But we can actually use these LSTMs to convert all of the experience entries in our resumes into a vector space, and then automatically that information is encoded within them. It's pretty incredible. And you can even, you can do like operations. So if you take the location in vector space for king, and you subtract the vector space for man, and then you add the vector space for women, so you're just adding and subtracting numbers, you end up at the word queen. So king minus man plus woman equals queen. Mark Zuckerberg minus Facebook plus Amazon equals Jeff Bezos. Exactly. So pretty trippy that like computers encode conceptual concepts in a very similar way to the human brain. QuickDraw is incredible. You should play with that at home. It's really, really fun. It basically ties together those two kinds of concepts. So it ties together the convolutional nets that we that are doing image recognition with these LSTMs that are recognizing words. So basically, and it trains as you work on it. So you're trying to draw a fire hydrant.
I see paint can, or camouflage, or pliers, or dumbbell. I see ice cream, or tub, or suitcase, or bed. I see beach, or helmet, or string light, or popsicle. I see stairs, or microphone. Oh, I know,
Damn.
It's fire hydrant.
Pretty cool, eh? Anyway, I won't continue doing that, but there's a lot of late hours that you can have at home drawing for a neural network. I'm glad I won. I'm usually terrible at that. Yeah, so basically, I just described what my company does. And we have over 30,000 candidates in our platform from across the US. They're mostly software engineers applying for jobs in the financial industry. And the cool thing about building models and learning from applications is that, one, you don't need a human recruiter phoning you up and providing you with the inside information. You can see it in this marketplace. It's open and visible. And then we can provide feedback on to both our candidates who are applying for jobs and our clients. So the candidates can see, for example, that there's an optimum number of words in an experience section, which happens to be 250 to 300 for those listening at home. And we can provide information back to clients like how responsive they're being relative to everyone else on the platform, how many of their candidates are interviewing elsewhere. And those kinds of statistics gamify the experience and hopefully pressure them into saying, oh shit, 40% of my applicants are interviewing elsewhere in the system. I should be making decisions quickly. We use a mix of Bayesian, multi-stage Bayesian regression models, which I talk about in this paper that I wrote, which greatly improves the model fit. And we also use an ensemble. And then we ensemble that Bayesian regression model with a deep neural net. In that deep net, for example, I think this URL went down. We switched from Amazon Web Services to Google Cloud, and I think this I think this server was a casualty of that recently. But basically, it allowed you to go and type in bullet points, and then it would output the chance that you had of getting an interview based on that bullet point. So if you sat around all day checking my Facebook feed, you predicted a 0% chance of interview. If you had this really good sentence, for financial clients looking for software engineers, then it predicted you had a 98% chance of interview. So pretty cool, pretty intuitive. And the predictions that the model outputs very closely match reality. So if our model predicts that you have a 50% chance of interview, you very likely have a 50% chance of interview. Finally, deep reinforcement learning is a really it's a burgeoning space in deep learning, and it was a large part of what enabled AlphaGo to beat the world's best Go player last year. It's what's allowed Google DeepMind's DeepQ learner to become really proficient at loads of Atari games. There's loads of videos of watching this DeepQ learner beat the computer at loads of Atari games. And the amazing thing is that they didn't feed any information, on how to win the game to the network. They just said, try to get more points, and over time it learns how to perform really well. OpenAI and Google DeepMind both provide tools for building those kinds of deep reinforcement learning models. And finally, I'm hiring. Untapt, we have 4 roles open right now. I encourage you to have a look on AngelList for the full kind of details, which for the engineering roles require you to apply via Untapt system, which I think makes good sense. For people here, the full stack developer role or the data engineering role would probably be most relevant. The data engineering role is working directly with me. We'd be sitting next to each other, and you would be. We're kind of imagining for that role somebody who has been a software engineer for a number of years, has a strong computer science background, and will be able to productionalize the kinds of the models that we're building. And in turn, you would be able to learn a lot about machine learning and how to build that into a production environment. So,
what are the percentages next to the cell?
Oh, equity.